All right, so Appendix A does relate a little bit to some things that we will have to do with our calculator, so I do want to get into that a little bit. It's page A-8, A-9. So I'd like to look at number 14. So Sam, if you would go into your graph screen, and if you would put into F1 here, number 14, it was x minus 2. Oops. There you go. X minus 2 plus 2 cosine x. Okay, and hit enter. Now, I want to show you something that's kind of interesting on a graph. Now, this graph happens to kind of show up in here. Now, if you're doing it on yours, your window may be a little different than this. Let me show you something that is real useful in calculus. Most of the time, we're given a domain to look at on a function. And in this particular problem, they said from -5 to 5. So go into your window, under the menu, the window and the window settings, and put in your x, min, and max of -5 and 5, and then hit OK or enter. And okay, and now you depending on what your y is and where the graph is, you may not be able to see the whole graph. And in this case, we're losing some of it down there at the bottom. So you could, there's a really cool little feature. Go under menu again to the window, and this time go to, okay, don't go to window settings, but go down here to zoom fit. Zoom fit. And what zoom fit does is it takes the x values between -5 and 5, a whole bunch of them, and it plugs those into the function, sees what the y values are, and then it sets your y window for you automatically so that all of the graph fits in the window. It's really cool, especially when you know what domain you want to look at. And most of the problems we do give us a certain domain to look at. So you go -5 to 5, you do zoom fit, there's your graph, you can see the whole thing. All right, so we're supposed to find the root of this function. Now the root is where f of x equals 0, right? It's where the output is 0, which is where it crosses the x-axis. Now, we're going to do that a lot this year, okay? Now, today, we're going to start talking about derivative, which is the slope function. And we are interested many times, if you look at this, hit trace on this real quick, okay? And just go up here to that maximum right there. Just trace to that maximum there. All right? And right there, okay, what's the slope right there at that maximum? What's the slope up there? 0, right? Now, remember we talked about max profit of the coffee mug? Remember that problem? We wanted to know how many coffee mugs should we manufacture to get the max profit? That's a typical calculus problem. We want to find the maximum. Well, the maximum is, one of the places to look for maximum is where the slope is 0. Okay? So we're going to be talking over the next several chapters about how to find a derivative function or a slope function. And what we'll want to know is where is that slope function equal 0. So now let's pretend that this is our slope function. We'll want to know where it's equal to 0. So we would want to know where it crosses the x-axis. So go ahead and trace back there, Sam. And the nice thing about this calculator is when you trace, it tells you when you hit a 0. Boom. There's 1, 0, 0. Now trace to the right. And there's another one when he gets there. There's another one right there, 1.109. And then there's another one over here. Go ahead and keep going to that last one. And there you go. And we know, because of that graph, we know those are the only 3 times that function is 0, has a root, because we can see it right there. All right, now, that's the advantage of a graph, is we know those are the only 3 times that it crosses the x-axis, the only time it equals 0. Now go to the calculator screen, just hit the scratch pad again, there you go. And now go under menu to solve. Another way we'll do this, I'll be honest, most of the time, because it's faster than graphing and setting your window, most of the time you guys will go to solve. Now since we've already entered into f1 of x, let's just, let's just type the equation. Type in x minus 2. We'll pretend we haven't even went to the graph screen. So x minus 2 plus 2 cosine x. Okay. okay, equals 0, and then comma x. Now, most of the time, we would do this. If we want to know where that equation equals 0, we would just go right to here because it's faster to graph and it's set in the window the whole thing. You go ahead and hit enter, and sure enough, there were our 3 answers, right? But look at this down here. Warning, more solutions may exist. You know, it may not find them all. And so there might be times where, and that comes up a lot. Now, just because that comes up doesn't mean there are probably more. I mean, a lot of times you can trust them. But it is something to think about. So being able to go to the graph screen and do it might be a good double check to see that, yep, there is only 3. All right, so I wanted to comment on that. Now, go back to your graph screen, and let's go into your F1 there, hit the tab, and let's delete that one out. Go up to F1, let's just arrow up. There you go. Delete that one out of there. And let's do number 29. Or, which ones did you do? 25 and 29? Okay, they're very similar. Let's do 29. Okay? So 1 over 1 plus x squared. And what we're into, okay, go ahead and graph that one. And what it's telling us, and this is something we're going to talk more about on Monday. But what they're telling us is we want to zoom in and look at this graph right there at the point 0, 1 until that line looks straight. And this gets to something we were talking about at the beginning of the year. We said, if we want to do the slope of a curve, how do we do that? Slope, we need a line. We need 2 points on a line. Remember when we talked about how if you took a curve and you took 2 points really close, wouldn't it look like a line? Right? If you took a curve, took 2 really close points and connected them, you're zoomed in, so it's going to look straight, even though it is curved. So that's what we want to do. So I want to show you a couple tools on the calculator to do this. So go to your menu and the window, zoom again, and this time we're going to choose zoom in. Now, choose zoom in and ask you where the center. So you move your cursor right over where you want to zoom in at, which here's at the point 0, 1. Go up a little bit, go up a little bit. Okay, and now you can either hit enter or you can push the middle of the trackpad, and it zooms in. Now, don't do it, but we could keep doing it. So you could keep zooming in, zooming in, zooming in. There's another thing that's kind of cool. Go back to your menu in your zoom window, and it's called Zoom Box. And you choose Zoom Box. Now it's kind of like dragging a box on your computer. You start in the top left corner, and you drag down to the bottom right corner. So move that thing up and to the left, about there, that's good. And then it's asking you for your first corner, so you hit enter. And now drag, whoops, a little too fast, drag down to the bottom right. So move over to the right a little bit. Okay, see how, so what you're doing is drawing a box right around where you want to zoom in. And what it's going to do is it's going to make that your new window, where that box is. So go ahead and hit enter. And it zooms in. Now, it doesn't look straight yet. We haven't zoomed in enough, so do it again. So you're still in the zoom box mode, so just come right up there. There you go, right about there is good. Hit enter, and drag down. Hit enter again, good. Now, I don't know if we're perfectly centered. It really wanted us to be centered in there, but that's pretty darn close. Now, that almost looks straight. I mean, you'd have to get pretty picky to say that's not straight. You'd see it's curving down at the end a little bit. You can do it one more time if you want to do it. But basically, the question is, what is that window? The question is, what is the window? So now just go to menu and the window settings. And so for number 29, you would just, oops. For number 29, you just write down the X, min, and max. There's that interval, and then the Y, min, and max, that interval. That's all you got to put. Okay? So we'll be doing that more next week. All right. Any questions on Appendix F? All right, let's look at Appendix F, or the worksheet maybe, Appendix F here, and worksheet we're on the trig stuff. So maybe, because we do have a lot to do on Section 1.4, so I would work one of these equations if you want. Otherwise, if you've got more questions on the trig stuff, we could, I certainly would meet with you sometime and go over that trig stuff if you need to. And we'll have opportunities to look at it again, but anybody got one? they want to see? If they want to see solved. Number four. Okay, that'd be a good one. All right, so we've got 2 sine cubed x equals sine x. Now the first thing I need to do there is what? Subtract the sine x over. It's very important that we get 0 on one side. Most of the time in solving equations, algebraic type equations, getting 0 on one side is a really good strategy. Now you could say you could divide both sides by sine. That gets you in trouble because you lose solutions possibly. So I would stay away from dividing both sides by sine. So what can we do after this? We could factor out a sine of x, which would leave us 2 sine squared x minus 1 equals 0, correct? Now, we've got 2 things multiplied equaling 0. What's that mean? One of them has to be 0, right? That's a special property that 0 has, right? I mean, no other number has that property. If this was a 6 over here, hopefully you wouldn't have left a 6 over there, in fact. But if 2 things are multiplied to equal 6, does one of them have to be 6? No, one could be 2 and one could be 3. One could be 12, one could be a half. 0 has a very special property, and that is that when 2 things multiply to equal 0, one of them has to be 0. It's called the zero product property. So sine of x equals 0, or 2 sine squared x minus 1 equals 0. So that one will leave. Here we'll add 1 to both sides. We'll divide by 2. We'll do what next? Sides. Of course, remembering that anytime you square roots, you have to do plus or minus. Now, what's another name for square root of 1/2? It's square root of 2 over 2. Now, the reason for that is because we can square root the top and square root the bottom. Square root of 1 is 1. When we have a square root of 2 in the bottom, we can multiply the top and bottom times square root of 2. And we get plus or minus square root of 2 over 2, which of course is one of our important, well-known trig values. And it's for what angle? 45 or pi 4, right? And what's the plus or minus mean? But I mean, as far as trig values, all 4 quadrants, right? Sine is positive in the 1 and 2 quadrant, and negative in the 3 and 4 quadrants. So we could be in all 4 quadrants. And so if you're doing a unit circle thing, that means you'd be 1, 2, 3, you'd be in all 4 quadrants. Which would be what? Pi fourths? Well, okay, let me talk about that a minute. Let's just give those 4. 3 pi fourths, 5 pi fourths, and 7 pi fourths, correct? And then when is sine 0? Sine is the y, right? And sine is, y is 0, either at 0 or pi or 2 pi and so forth. If we just look from 0 to 2 pi. Now, I'll be honest with you. If that pi n, 2 pi n business bothers you, don't worry about it. We don't deal with it very often. Now, the calculator shows up, so we do have to understand what it means. But most of the time, we're given a specific interval. So if we were given, like we were on the last 4, 0 to 2 pi, with the 2 pi not included, our answer would be 0, pi, and then all 4 of these, right? Those would be our solutions. We'd have 6 solutions, right? But because they gave it to us that way, well, this is going to be 0 pi, 2 pi, 3 pi, 4 pi. This would be 0 plus pi n, which is just pi n, of course. And then this would be what? Yeah, since these are all evenly spaced, they're all what? 2 pi fourths apart? And it just keep going. 9 pi fourths, 11 pi fourths. They're all 2 pi fourths apart, which is pi halves. So you could go pi fourths plus pi halves n, right? And that would get all of them. Or you could do pi force plus pi n and 3 pi force plus pi n, and that would get them 2, right? I mean, but again, that's a small part of what we do. So let's look. I'm just curious, what would that look like on the calculator? Because again, why do we need to solve these? Well, remember what I said a minute ago. We're going to be looking at places where the slope is 0. It's going to be one of the main things we look at with derivatives. Where is the slope equal 0? Well, let's pretend that this function right up here was our slope function. We'd want to know where it equals 0, because those would be possible places where we have a max or a minimum. So we would need to solve this. Now, it might be a calculator problem, might be a no calculator problem. If it's a no calculator problem, we've got to be able to do this. If it's a calculator problem, Sam, you're up again. Let's go to the calculator screen. Go to your calculator screen. And let's solve, and let's type this in. 2. Now, how are we going to do sine cubed?
Outside.
We tried it last period, so for sake of time, we won't do it. You cannot put that cubed where we write it. It won't understand it. Okay, what does sine cubed mean? It means that. Now, we got to be a little, I think that'll work, but that always makes me nervous that it's just going to cube the x and not the sine. So I always get a little nervous about that. So if I was doing it, I would probably move the cursor inside of that and hit a right parenthesis. Just hit the right, and that would be bad. Why would that be bad? Yeah, that's no good. We better come back here to the 2. We don't want the 2 to be cubed. So go, yeah, there you go. Hit a left, there we go. And then I would delete that cubed. I think the way you had it, Sam, would work. Let's hit delete again. There, and put it right there. There we go. So see how we've sub sine of x, then in parentheses, and then the cube? I don't think it is. I got sine x, and I got this parenthesis, so I think I'm okay. I don't think it's cubing the 2. All right, so now I got 2 sine cubed x minus sine x. Yeah, because this is my solved parenthesis there. And nice thing about when it puts that extra parenthesis in there for you, you never are short of parenthesis, because usually if you hit a left, it'll give you the right. Okay, now go ahead and hit enter. Okay, now look what we get. Now forget the n7. It can be n1, n2. It doesn't matter. It's just n. Just treat it as n. Look what we get. We get pi force plus 2n pi. Okay, well that'd be this one. Okay, and then arrow up here. See, it doesn't simple. It's kind of, you think a calculator this smart would have figured this out, but it didn't. Look at what we got here. We got 3 pi force plus 2 pi n, so that'd be that one, and then all of its combinations. Keep going. And I'll bet we're going to get 5 pi force plus 2 pi n. Okay, keep going. Is that it? What about 7 pi force? Oh, wait a minute. Back here. Back up here. I think we missed something. Because I see a 2 pi n minus pi force. Yeah? Right here. Right here. 2 pi n minus pi force. Which one would that be? Isn't that the 7 pi force? That'd be 2 pi, 8 pi force minus pi force. That'd be the 7 pi force one. And then scroll back over here. And then we had the 5 pi force plus 2 pi n. And I don't know why it didn't give us as a 7 pi force. That's interesting. And then this one was the pi n, which was the other one we had. So it gave all of them to us. But whenever we get that pi n stuff, it always looks weird. Yeah.
What are all the n1s and n8s?
Well, every time you do a new problem, it treats that as a new constant. So it calls it N9 and then N10. I think if you cleared Scratchpad, it would go back to N1 again, I think. So it doesn't want you to think that this N in this problem was the same as that N in the other problem, I guess is what it's doing. Okay? And this one, see, this is a different N than the one over here. So that's why this one's N8 and this one's N9. Okay? Just don't worry about that. That's no big deal. Okay, now, what we normally want to do, so Sam, go up and grab this, arrow up and grab that, hit enter. Now, what we normally want to do is we want to tell it we only want to look from 0 to 2 pi, because most of the time we have that restriction. So what I think I showed you this the other day. This is where the vertical bar, did I show you that? I never showed you the vertical bar? Okay, so right under here, so we go outside of the solve, go outside the last parenthesis. And this is something we use quite a bit. You go outside the last parenthesis, you hit Control equal, And this vertical bar right here. Now, you can't use that for absolute value, okay? That's not a vertical bar for absolute value. But we get that vertical bar, it means with or such that. It means we want to solve this such that our x is between there. So now you're going to type 0, then hit Control equal again. We want it to be between here, which means we want 0 to be less. Oops, I'm sorry, don't hit enter yet. Okay, we're going to hit Control equal. We want less than or equal to, then x, and then we want it to be less than 2 pi. So Control equal again, less than, and then 2 pi. So see how we told it we want it to be between 0 and 2 pi. We want to include the 0 but not the 2 pi. Now hit enter. And then it gives us just those answers. 0, pi fourths, 3 pi fourths, pi, 5 pi fourths, and I think if you keep going, it'll give you 7 pi fourths, I believe. Arrow up there, just to see. Yeah, there's 7 pi fourths. So it gave us 0 pi, didn't include the 2 pi here. We didn't want that. And then, okay? All right. So some calculator stuff to solve those equations and also to solve them without the calculator. All right. Let's move on to chapter 4. Open up to page 35, please. I think you're off the hook now, Sam. Thank you. Good job. All right, page 35. Okay, right down at the bottom is section 1.4. Now, welcome to calculus. You're ready to start. Did it have a new pencil to start this? Okay, good. Yes. Sharpen your pencils. New piece of paper. What else? Maybe you should bring out a new pencil, brand new pencil. Okay. The derivative of f of x has this notation right here. We read that as f prime of x. F prime of x. That little slash means we read that as prime. F prime of x. Okay? Now, what that means, that really means two things, and we're going to talk about both today. They're the same thing, but it's two different ways of thinking about it. One way of thinking about f prime of x is the rate of change of f of x. For example, miles per hour, dollars per mug, etc. A rate of change. A rate. Okay? So in that case, F would be miles, or F would be dollars. Now keep in mind that the authors of the book think that this is the first time you've ever heard of rate of change and derivative. They don't know that we spent 4 days last week doing those exploration worksheets and talking about this. So hopefully some of this that we're talking about here today makes sense and you can connect it to some of the stuff that we did last week when we were kind of looking at the overview of what we'd be doing. Okay? So when you read some of this, that is in the textbook, it's explained as if this is the first time you're hearing about it. But remember the balloon problem with the altitude graph, and then we had the velocity graph right next to each other? We were comparing those two. That's the kind of stuff we're talking about now in this section. So hopefully you can grasp onto that a little bit, and it's not totally new. All right, on page 36, so in the blue box in the middle of page 36, it has this description. It says f prime of x is the instantaneous rate of change. Not average rate of change, that's slope between 2 points. We're talking about, remember the door opening? We want to know how fast is that door opening right at 1 second? How fast is the balloon rising at 1 second or at 1 minute or whatever? Instantaneous rate of change. Now the other way to think about f prime of x is the slope of f of x. The slope of f of x. If you had a graph that had no units on it, no story problem attached to it, it would still have a derivative, which would be the slopes of the original graph, the f graph. Okay? So we often talk about these functions as an original function or an amount function, and then its derivative, or its rate or slope function, right? So we have an original function f and its slope or rate function f prime. So the original would be like the amount of miles you travel, the amount of dollars that you make on the mug. And then its associated derivative would be the dollars per mug or the miles per hour that you travel. Now sometimes we will use you don't have to write this part down. Don't write, I wouldn't write this. Sometimes we leave off the x. We just talk about f and f prime. Because the input doesn't really matter. I mean, it matters. But what's important is the name of the function. For example, if I give you the function f of x equals x squared, or if I gave that to you as f of t equals t squared, or f of z equals, aren't those the same? I mean, if I told you to graph these, wouldn't they look the same? They'd be parameters, right? Like on a calculator, you have to put in x, right? Even if the function is t or something else, right? That doesn't matter. Matter of fact, if I ask you, what f of German short hair, right? That first one's kind of bad. That one's kind of bad. But, right? I mean, that would be a function. That means, right? I mean, the input is just saying, a function just is a rule. It says whatever your input is, you square it, and that'll be the output. Okay? So that input number doesn't really matter. So a lot of times we just talk about f and f prime, and talk about it that way. All right. But again, just so when you see that notation, it doesn't bother you. All right. So rate of change, slope, they're the same thing. So we've got a nice example here at the bottom of page 36. If you would read that in the italics about noon on October 1st, 2000, just read that to yourself real quick. Okay, now, up on the board here, I've got, underneath here, I've got, all right, these graphs. So P, they're going to call the P function the position of the car, what's it talking about? At a certain time, and it's where? It's the position east of the capital. It's where the car is, east of the capital, is this function. okay? And so it would be in miles. Input would be in hours, okay? And then V is going to be the rate, the velocity of the car, the eastward velocity of the car. Now, those guys in physics have a little bit of an advantage, okay, maybe on this whole idea, but it's the eastward velocity. So let's say going to your right. Well, we'll get into acceleration in a second, but that's just velocity, okay? Now, we know now, by looking at our new notation, that these two are the same thing, right? Isn't velocity the rate of change of your position? Remember, we talked about it being the slope, so it's the miles over hours. It's the same thing we talked about with the door, degrees per second. Remember that? The balloon was vertical feet per minute or whatever. So these units divided by these units would be the slope, miles per hour. So the velocity, that's the rate of change. So velocity function is the same as P prime. Those are saying the same thing. Okay, P is the position, V or P prime is the velocity. Okay? All right, now one of the things you will have to do on your next quiz is you will be given a problem in context like this with the functions defined, very much like that. And then I will ask you a question something like this. In the context of this problem in the car in Bismarck, North Dakota, what does that mean? Somebody want to take a crack at that?
2 hours, 100 miles.
That's pretty close. It's really close. I want you to be a little more specific about the 2 hours.
2 hours actually.
And when was departure? Noon. So how about at 2 p.m.? That'd be better, right? 2 hours after noon, that'd be good. But at 2 p.m., at that instant, the car is east of Bismarck, of the on-ramp at Bismarck, right? The capital. Now, good job. Somebody might have been thinking this, because several people in the other class said this. Several people said at 2 o'clock, you've traveled 100 miles east. That's not quite right. What does it say? Does it say how far you've traveled? What's it say? It's just where you are. It's your position. Right? You could have went 150 miles east and then come back. Right? I mean, just based on this, not the graphs, but just based on this. This is at 2 o'clock, you were 100 miles east of Bismarck. Now, what if that 100 would have been negative? You're west of Bismarck, right? Position could be both positive and negative. So 100 would be east of Bismarck, negative 100 would be west of Bismarck. Okay? Now, does it tell you, just this alone, tell you anything about what direction you're traveling? It just tells you where you are. It just says at 2 o'clock you're 100 miles east. You could be going east, you could be coming back west, you could be stopped and having lunch. It doesn't say. Right? Now, if we go look at the graphs, then we got more information. But if I just tell you this, I'm only giving you a point on the position graph. It just tells you where you are. Okay? Now, so that's about all we can say with that. So now let's say I told you your velocity at 2, which, by the way, is the same as saying P prime of 2, correct? Those are the same thing. Again, when you see that prime notation, you think rate of change. In this problem, we would think rate of change because we have units to go with it. We're not thinking slope here, we're thinking rate of change. When you see P prime, you think rate. So this is the P units, which were miles, divided by hours, right? Because it's a rate, so it's miles per hour. And what if I told you that that was 70? Tell me what that says. At 2 o'clock, you're going 70 miles per hour eastbound because it's positive. Since that's a positive 70, we're eastbound at 70 miles per hour. And if you combine it with this, we're 100 miles east, going 70 miles per hour in an eastward direction. If this was negative 70, we'd be 100 miles east, traveling west at 70 miles per hour. Right? There you go. That's what's going on with this notation. Okay, so you're going to have some questions about that those kind of things. Now go up top page 37 and now look at these actual graphs. Now I don't have a picture of this, so we'll. I apologize to those of you viewing at home, but you're not going to get to see this. But it's on the book on page 37. Oh, I got to turn this thing on. First time I used my handy dandy camera here, but okay. Whoops, scoot down over. All right, there we go. Now I get to use this. All right. I use my point on it. Now, tell me if I get it right here, Tim. All right. So at 2. So looking at 2, and we look at the P graph, and what do we see? Is it about 100? Pretty close. Now, since we have the graph, we know more than just that point. What's the graph doing that tells me we're headed east? The graph's going up, which means the slope is positive. So now I'm thinking about slope now, right? It's the same thing. Slope, rate of change are the same thing. Okay? Since the graph's going up, it tells me I'm going eastward until what? About 3? And then I stop and come back west. Now, I've asked you this before last week. I'm going to ask you again. Over here is the V graph. But now, what other name could we give to this graph? No, not acceleration. The P prime graph. This is the P prime graph, which is the slopes of the P graph, right? So this graph is plotting those slopes, right? And we're going to get into that more over the next couple days. But right here, the P graph, if this is P prime is 70 at 2, then that tells me that the P graph has a slope of 70. So let's look at that and see if that's reasonable. Now you're going to do this in your homework. You're literally going to come in here and draw a line. I bet somebody's already drawn it in there for you in your book, have they? Maybe not. If you want to in pencil, if I drew a line right along here, a tangent line, over 1, up 70, I don't know, you'll get a look at that a little closer in the homework. Okay? And then if I come over here at 2, what's my y value? Appears to be about 7. Now, I want to ask you this. During these whole 3 hours right here, when this graph's going up, what do you notice about the 3 hours here on the P prime graph? Careful now. It's not constant. That's right. The speed's not constant, is it? And that's because this is curving. It's going steeper, then it's less steep. But this graph's going up when this graph is what? See, everybody always wants to say going down. I heard it, though. It's positive. That's one thing that's very important for you guys to get straight. And we'll have a long time to help get that straight because I'll be hammering it over and over and over. When this graph's going up, this graph is above the x-axis. It's positive because this graph has positive slopes, and right here is a plotting of those slopes. So we're plotting positive values. It's above the x-axis. When this graph's going down all the way to about 6.5, this graph is negative, below the x-axis. Now it goes up some and it comes down some, but that's related to the fact that this line gets steeper and then it gets less steep and then it gets steeper and then it gets less steep. That's why this goes up and down. Because the slopes get more and then less and then more and then less, right? And then here the graph goes up, and what do you got over here? Positive, above the x-axis. Right now, I don't really care that this graph goes up and then down. I don't care. I just care that it's above the x-axis. This graph's positive, where this graph's going up. We're getting a little ahead of ourselves. That's something we're going to do in section 6 a lot, is these connections between the two graphs. But I'm just giving you a taste of thinking about that right now. Okay? But I want you to understand the notation, what it means, okay, and be able to talk about it in that way. Okay. Back to our screen. So there is some good stuff to read there. On page 37, they do a pretty good job of explaining most of what we just talked about. Over onto page 38, they talk about it some more. We're going to skip to the top of page 39. Top of page 39 is when they say, okay, this F prime business also means not only rate, but slope. So in the blue box of page 39, they give the idea that it could be slope. So we might have a problem where you have a graph, no units, no context of a story or anything, and we just say, okay, this, like we were just talking about, where this graph's going up, has positive slopes, the F prime graph would be positive, have positive y values, positive outputs, okay, and that sort of thing. Okay, so we'll get into that a little more. Now, somebody brought up acceleration. We could go one more derivative. Now, we're going to get into that more in section 7. But you could call velocity your original graph, and you could do the derivative of velocity. Now, I think I've run out of room over here, but the derivative of velocity would be v prime. Well, if you put a prime on v, what would this be? P prime prime? We'll call it P double prime. We'll call it P prime prime. We'll call it P double prime. That's called the second derivative. But we'll get into that later. But think, what would it be? Well, it would be the rate of change of velocity. Well, what is a change in velocity? That's what acceleration is. And the units on acceleration are miles per hour. It's these units divided by these units. Just like when we do the derivative of p, position, which is velocity, which is miles, our units are miles per hour. When we do the change in velocity, it's miles per hour, and it's the same concept. Now, a lot of times we say miles per hour squared, but I think miles per hour is more indicative of what's happening. You're changing your miles per hour at a rate every hour. So, yes?
So, derivative for velocity, would it also be just a graphing of the slope of the velocity graph?
Same exact thing. The acceleration graph, P double prime, would be a graphing of the slopes of the P prime graph. Exactly. Absolutely. And we can get third derivatives and fourth derivatives. Quite honestly, in most actual applications, first and second derivative is enough. Very seldom do we need more than that, and we rarely talk about it. Okay? All right, turn to page 40. And we've got this picture here. Okay? And we've already visited about this a little bit. When we talk about the slope of a curve, okay, since we're talking about f prime being a slope now, what's that mean? Well, it means the slope of the tangent line. You can't really do slope of a curve, you can only do slope of a line. Well, what we mean by slope at this point, or slope at this point, or slope at this point is the slope of that tangent line. So there are going to be some questions on the homework where they have you write the equation of those tangent lines. Well, how do you write the equation of a line? Or point slope form, right, great. And what do you need for that? 1 point and the slope. If you have 2 points, great, you could calculate the slope. But usually, look at these tangent lines. How many points do you have? They only have 1 point. So you have 1 point and you need the slope. Well, how do we get the slope? Well, right now we'll just do rise over run. Probably on some of the problems, you may just have to sketch a tangent line like this. Actually, on our next quiz, you will do that. I'll give you a graph like this. I'll say find the slope at 1, approximate the slope at 1. You'll come on that graph and you'll actually sketch a tangent line, and you'll draw yourself a little slope triangle and do a rise over run. Just do a rise over run, estimate. And then everybody's will be a little different probably, you know, because you're all drawing it a little differently. But I'll look at your picture, I'll look at your slope triangle, see if it's reasonable, and that'll be good enough. So for right now, that's about the best we can do, is we can just estimate the slope kind of with a rise over run kind of thing. So that'll give you the slope, and this is the point. They usually tell you what the point is. You plug that into that y equals m times x minus x point plus y point, and boom, you got it. Equation of tangent line, easy. Okay, so there'll be some of that on the homework as well. All right, let's move on here then. There's 2 last kind of applications of this idea that I want to do, and then give you some work time. So let's go back to this page. Okay. Leave that up there. Let's get rid of this. Okay. So first kind of application of this. Oh. Well, for those of you watching, there's some stuff written there, but you can't see. Okay, so the first thing is free fall. Applications of free fall. Okay, I'll leave that up there and you guys can see if my marker misses it. Yeah, it's just, it's kind of, okay. It's kind of in the wrong place. Okay. Not bad.
It's just a mystery.
All right. So,
It's just small.
you almost want to skip class just to watch the video. Okay. So, so free fall, application free fall, which means you throw the ball up in the air, right, and then it's just acted on by gravity alone, right, or you drop something, right. That's what we're talking about. Now, there's two equations we want to use. Now, later on in the year, we'll talk about how calculus is where these equations come from. But for right now, we'll just write it down and use it. So, the height of an object in free fall, we'll call that function h of t. And it is negative 16t squared plus v sub 0 t plus h sub 0. Now, t is the input variable. V sub 0, you probably know this from physics. I think in physics you call it v sub I. Initial velocity. Okay? So if I throw the ball in the air, or if I throw it down, it would have an initial velocity. If I just drop it, 0 would be the initial velocity. Okay? H sub 0, the initial height, or the initial position of the object. So if I drop it from 6 feet, 6 would be the initial height. And then that negative 16 comes from the fact that the acceleration of gravity is negative 32 feet per second. So it's half of that. If it was a meters problem, if the problem's in meters, then it'd be half of, what is it, negative 9.8? So just and this is in your book on page 41 over there. If it's a meters problem, just substitute negative 4.9 in for the 16. Okay, I think the problems in the homework are in feet. Okay, so I don't know, science and math can't get together. Math
You
puts,
memorize my physics.
well, yeah, math homework we always use English units, and science we always use metric. And so I don't know why that is. Well, I'll be honest. You guys are too young to remember this, but well, way too young. In 1980, yeah, in the late 70s, there was a big push to switch everything in America to metric. And so whenever, anybody got a water bottle? I mean a water bottle with, here. I think there's one in the trash. Right here. Right here. So that was when you started getting on the labels 20 ounces and then in parentheses 1.25 pints. Oh no, that's English. And then 591 milliliters. So they started putting both, because the idea was, and I was about your age when this happened. Because I was a track runner, and my freshman year, it was the 2 mile, it was the mile, it was the 440 yards, it was 880 yards, right? Everything was in yards. And the state track meet in 1980 was the first year switched to metric, 400 meters, 1,600 meters, and so forth. And that was part of this whole push to turn everything metric. So for years they thought we'll transition, we'll put, like on the speedometers on the cars, right? It has miles per hour, but then underneath it, it's got kilometers per hour too, right? And that is still left over from those days. They thought, well, we'll transition, we'll put both, and then eventually we'll go all metric because the rest of the world is all metric. But we're stubborn in America, and we think we're kind of better than everybody else. And so we just refused. I mean, people just refused to convert to metric. And so it never, they tried to make it a law, they tried to make it happen. I think it is a law that you have to put both on the labels and stuff, that's why they do it. But they just were never able to get us to switch, and so now we're kind of left in this limbo where we use both. But all right, so we can do whatever we want. All right, so there is the velocity equation, and again, if you're going to use metric, if it's in meters, then the 32 would be 9.8. So that's velocity, which of course velocity would be another name for the v function here. H prime. H prime in this case. The change in height would be the velocity. Okay, so we could call that H prime. All right, so there's a problem there. It's example 4. Talks about trying to throw a ball to the top of the Metrodome in Minneapolis. And could you reach it if you threw with this initial velocity and from this initial height, you just plug those numbers in. It's pretty simple, really. You use your calculator. I think in the homework problem, they reference example 4. They just change the numbers a little bit and have you plug those in. So it's pretty easy as long as you know those are the equations you're supposed to work with. All right, so that's the first thing. The second thing, and then we'll work on the homework, is this thing called the speed limit law. The speed limit law. Okay. Now this is kind of tough. This is kind of technical language. We're gonna write it out, and then we're gonna talk about it in more common, ordinary language and make sense of it. All right. Here's what it says. Let f be defined for all x in the interval AB. Okay, so that just means that f is nice and smooth and no holes and weird things going on. It's defined interval. Okay, in some closed interval. If f prime of x is less than or equal to m for all x in AB, then f of b minus f of a is less than or equal to m times a quantity b minus a. Obvious. Right? Who doesn't know? Now, let's make sense of that. It's really an important idea. Actually, once we put it into ordinary language, it'll seem like a very simple idea. Okay? But this is the technically mathematically correct language. So let's start up here. What's f prime? What have we learned f prime is? Rate or slope. We're going to talk about it both ways. Let's start with rate. So let's think of it as a speed. Okay? The thing is a speed. Speed and velocity technically aren't the same thing, but for us right now, it'll be fine. Okay? So f prime is speed. So if our speed is less than or equal to some number m, I left out the part where it says m is any real number. Okay? So if our speed is less than or equal to some number m, let's say our speed is less than or equal to 100. What could I call m? What would be a name I could just give m? If our speed is less than or equal to 100, then what could we call 100? Our speed limit or our max speed. How about that? Let's call it our max speed. Okay? So let's call m our max speed in this case. Isn't that what that's saying? It's saying if our speed, if our rate of change is always less than or equal to m, then what that's saying is m is our max speed. Okay, so now let's come down to this line. So m is our max speed. That's the fastest we're going to go. Let's say it's 100 miles an hour. Now let's talk about f of b minus f of a. Now let me make a little graph here of f to make sense of this a little bit. Here's a, here's b, and let's say the output on the f graph is there and there. Now, what name would I have, what notation would I have for the output at A? Come on, this is why we did sections 1, 2, and 3. F of A, F of A. I mean, that's simple, right? I mean, that's what the output of F at A is. It's F of A, right? And what can I call the output of B? Oh, way to go. Good job. All right. Awesome. F of B. You guys are quick learners. All right. So, y value f of a, y value f of b. Okay? Now, remember, we're talking about speed here. So this is going to be miles over here, and this is going to be hours down here. Make sense? All right. So what is f of b minus f of a? It'd be this minus this. What would that be? It'd be like a distance we traveled, right? Well, it'd be be displacement, really. I mean, it wouldn't be the distance. We could have went west of Bismarck, then back east, right? Whatever. This just means we ended here, we started here, so that'd be the displacement, right? From where we started to where we ended, right? We'll just assume to make it easy, we're just going one direction, we're not going back. Okay? So this over here would be the distance we traveled, right? So this side would be the distance traveled. Would be less than or equal to, and what did we say m was again? Max speed. And what would b minus a be? Wouldn't that be the time we traveled? Right? So that'd be the time we traveled. That's just distance equals rate times time. That's all it is. That's all this is. It's actually distance less than or equal to rate times time. Because our rate isn't really the rate we traveled, it's what? M isn't really the rate we traveled, it's our max speed. So here's what this is saying. So this, for a speed limit equation, example, this is what it's saying. It's saying if M is the fastest we travel, let's say 100 mile an hour. So if we know 100 is the fastest we went, and we also know we went for 2 hours, what's that tell you? The most you could have went is 200 miles. Isn't that what that says? That the distance we traveled has to be less than or equal to 100 times 2, 200. That's what it says. If you travel for 2 hours, you know your max speed is 100 miles per hour. You know the most you went is 200 miles. Speed limit law. Let me say it one more time. So the speed limit law says, if you know how fast you're going, then you know how far you travel. Make sense? Makes perfect sense. Okay? So what it does is it connects rate to what it does is it connects the f prime to the f. It connects the rate function to the original function. Okay? If you know how fast you went, then you know how far you could have gone. Now let's talk about it with slope. Right? Let's talk about it with slope. Now I don't want to. All right. What happened? Okay. Weird. Yes. So let's talk about slope. So here's an example problem you get on the homework. If f prime of x is less than or equal to 3, I'm going to tell you that. Now let's think, not rate, but let's think slope. So what is that saying right there? Slope is, the max slope is 3. There you go. Now, instead of max speed, m is going to be our max slope. So if we know for this function, the max slope is 3, okay? And I'm going to tell you where I start. Let's say f of 1 is 2. You tell me about f of 5. I don't know about equals. Let me cross out that equals. If I know I started at the point 1, 2, and I know my max slope is 3, now I think a graph could be helpful. I'm going to plot that first point, 1, 2. This is my f graph now. So if I start at that point right there, you tell me about the output at 5. Would it be 14? It can't be greater than 14. Where is 14 coming from? Natalia, you said 14.
Because you have the 2 already, so you know that's that. And then 3, and you get a 4.
Isn't it a rise over run thing? I don't think it'd be 17. Well, wait. Here's the way I think of it. If the max slope is 3, doesn't that mean every time you go over 1, the most you could go up is 3? How many are we going over?
4.
We're going over 4. What's the most we can go up? Isn't the most we can go up 12? And we're already up 2. So doesn't f of 5 has to be less than or equal to 14? So what does that say? That says if you know the max slope, if you know the max rise over run, and you know how far you want to run, you know how far you can rise. Make sense? If you know the slope, but again, slope is really how fast the graph goes up, isn't it? Slope is really speed. The steeper the line, the more the slope, right? So slope is really speed. That's why these are connected. So if you know how fast the graph is moving, then you know how far it can possibly go up. If you know how far over, you know how far it can possibly go up. Another way they might ask this, instead of just saying, what can you tell me about f of 5, they might say, can f of 5 equal 20? They could have said, could f of 5 equal 20? In this case, you'd say no. Because if the max slope is 3, then if you go over 4, the most you can go up is 12. You were at 2, so the most f of 5 could be is 14, so f of 5 cannot be 20. Make sense? That's the speed limit law. So it's really, it's a lot of mathematical gobbledygook there. But it's basically saying, if you know something about the slope, then you know something about, or the rate, you know something about how far it moves. Connects f and f prime. All right, that's called the speed limit law. So you'll have a homework problem. I think it even says hint, use the speed limit law. Okay, that's the idea of the speed limit law. All right, you've still got, hopefully we got a little 20 or so minutes. We're going to work on 1.4 homework. Okay, it's going to be about notation. There's a few questions about this free fall idea. There's going to be a question or so on this speed limit thing. Some of the questions seem quite easy, I hope. It's just notation. It's going to ask you about p prime of 2 or whatever, and you're going to say, oh yeah, that's the speed, or that's how far east, or that, you know. Don't make it harder than this. It seems like an easy question, probably is. Here's the answer book. If you want to look anything up, be sure to ask me if you got questions too.